Hello, and welcome back to New Scientist Weekly, your curated selection of the week's science stories. I'm Christy Taylor in New York.
And I'm Sam Wong in London. Welcome to the show.
It's episode 208, and the team has so much to tell you this week.
Some physicists are claiming to have achieved a long-sought breakthrough in superconducting. We'll look into whether it stands up. We'll also be diving into the effort to save coral reefs from the hot tub-like sea temperature around Florida.
Plus, how stars twinkle on the inside, don't we all? And why we're all so bad at guessing how heavy our hands are, which is a math problem that I honestly had never thought about before today.
First up, New Scientist reporter Michael LePage is here to tell us about a development that could lead to better treatments for a wide range of conditions and also make those treatments much more affordable. It sounds a bit too good to be true, so tell us about it, Michael.
Yeah, so what we're talking about is a way of delivering messenger RNA or mRNAs to the blood stem cells in our bone marrow. Now that might not sound like a big deal at first, but it really opens up so many possibilities. As one of the researchers said to me, the sky's the limit. So we're talking here about treatments and even cures for sickle cell disease, for beta thalassemia, for those bubble boy immune diseases, for infectious diseases like HIV, and even treatments for aging. Oh, and if I were a sports person interested in cheating, I'll be really excited about this because there are all kinds of ways it could be used for enhancing performance, and they'll be really difficult, if not impossible, to detect.
That sounds really exciting, but can you break it down? How does delivering mRNA to stem cells help us do all these different things?
Okay, so to understand why this is a big deal, we've really got to go back to basics. So all the drugs we have at the moment are these small little molecules, and because they're small, they're not very specific. They often bind to the wrong target, they cause side effects, and what they can do is very limited. So what we really want are drugs that are made out of proteins, which are these big molecules found in our cells that can do pretty much anything. So for example, if you can get the proteins needed for CRISPR gene editing inside cells, you can fix disease-causing mutations.
So we're kind of using the machinery of our cells for what it's already good at. That really makes sense. Why aren't we already using proteins as drugs, though, Michael?
Well, we do have a few, but proteins are really expensive to manufacture, and they can't get from the bloodstream inside of cells. But mRNAs are the recipes for making proteins. They're really cheap to make. Now, if you just inject RNAs into the blood, they get chewed up pretty quickly, but if they're encapsulated in these little fatty particles, they can survive and get into the cells, and then the cells start making these proteins. And this is exactly how the mRNA COVID vaccines work.
Why can't we just use the vaccine technology, though, to deliver mRNA to the bone marrow? What's the problem with that?
Well, the issue is that if you inject these nanoparticles into the bloodstream, our liver mops them all up and takes them all up. So that's fine if you want to treat liver diseases, but it's no good for treating sickle cell disease, say, because you've got to modify the blood stem cells in the bone marrow. So the new thing that this team have done is they've attached antibodies to these fatty nanoparticles, and these antibodies bind to the surface of the blood stem cells, meaning that lots of these nanoparticles get taken up by the blood stem cells and get the RNAs inside them. And so this team have proven that it works in several ways. So one of the things they did is they put mRNAs coding for a glowing protein in these nanoparticles and injected it into mice. And then they showed that the stem cells in the bone marrow of the mice sort of lit up afterwards with these glowing proteins.
Are there any kind of potential unwanted effects of this kind of protein delivery?
There doesn't seem to be anything too serious. So one issue is that the nanoparticles do still get taken up by the liver. But for most purposes, it doesn't matter if you treat the liver as well as the bone marrow. And when it does matter, there are some ways around this issue.
It sounds amazing. I know there are already treatments that involve manipulating the bone marrow, but for those, you have to take the cells out of the body and manipulate them and put them back in, right?
Yeah, so for instance, there's now a CRISPR gene editing treatment that can actually cure sickle cell disease. But the problem is it's always going to be really expensive because of this need to take each individual's blood stem cells out of them, to edit them and grow them and stick them back in the body. That's really complex, difficult procedure. And basically that means that even people in rich countries may not be able to afford this treatment, let alone people in poor countries. Now, with this new technique, it might be possible to treat conditions like sickle cell with a single one-off injection. You just go into the hospital, get an injection, go home.
That's really exciting, especially the accessibility implications of this. Could this approach work for other kinds of cells besides the liver and the bone marrow also?
Yes, absolutely. In fact, this team have already shown they can deliver mRNAs to the immune cells known as T cells, and they told me they're working on all sorts of other tissues as well. So it's really exciting. I mean, I've been writing articles for years about CRISPR and mRNA technologies and saying that these things could do all kinds of amazing stuff if only we could solve the delivery problem and find the ways to deliver them to the right cells in the body. So it's really exciting to see this happening now. Of course, it's going to be a few years before we see the first trials in people, but I've got no doubt this is going to be huge and transformative.
Now we've got a story about a big claim and no small amount of controversy in materials science. Maybe you saw it this week. Researchers claiming they've managed to make a superconductor that runs without resorting to extremely high pressures or very low temperatures. Carmela Padovich-Callahan, this sounds like it would be an incredibly big deal if it's true, am I right?
Very much so. I think a lot of folks will tell you that it'd be nothing short of revolutionary. A room temperature, room pressure superconductor could make the electrical power grid far more efficient, environmentally friendly. It could supercharge magnetic levitation like what we use for super fast trains. It could help us make MRIs cheaper and smaller. It could even be used in nuclear fusion and the way we manufacture quantum computing hardware, which is a huge challenge as is. And it would also mean that physicists have cracked a problem that has been eluding them for decades. I used to be a condensed matter physicist, and this kind of superconductivity is a sort of a holy grail problem that you'd hear everyone talk about, like first-year grad students or physicists who've been in the field for decades. This is what people wanted to figure out. So it would be huge in industry and huge in science if it actually happened.
Yeah, and you just named a bunch of very futuristic sounding technologies that we could achieve with this. But what is a superconductor in the first place? Can you remind us?
Yeah, right. So the key idea is that if you have a material that superconducts or it becomes a superconductor under some conditions, then you can pass electricity through it without encountering any resistance. And this means that you're also not wasting energy. So think about putting your hand onto a piece of electronics and finding that it's warm. The warmth that you feel is really energy that's been wasted in the process of pushing electricity around. So we would cut down on this problem significantly if we could just replace most regular wires with superconducting wires. And that's sort of just like the first very naive application this could have. But as you mentioned, there is sort of a catch here. Physicists have known about superconductivity for more than 100 years. It's a classic discovery, but we've sort of not been able to make this work in any practical way. We can make superconductors, but they have to be either under extremely high pressure, sort of pushed between two diamonds, something you would definitely not do in your house, or they have to be extremely cold. So again, you need sort of liquid helium or something like that, which is it's not just costly, but also impractical for most devices.
Yeah, I don't know how I feel about having liquid helium in my home.
I mean, you could also have a giant fridge. That would also work.
But that sounds like it comes with its own energy cost, too. So let's get to the new discovery. This week, a research team shared some data that seemed to suggest that more convenient superconductors, room temperature, ambient pressure, may be just around the corner. So what exactly was their claim?
Right. So there is a set of papers on the preprint service called the Archive, where the researchers reported on a material that does seem to superconduct at room temperature and ambient pressure. This is really what you would want for a practical superconductor. This is how you would get all these benefits if you could make it work under these very ordinary conditions. But it's just 2 papers on the Archive right now, so it's stirred up quite a bit of controversy.
Yeah, so these papers haven't been peer-reviewed, right? But you spoke to some researchers who had early impressions of the work. What did they make of it? Did they have a view about whether this material really is a superconductor?
I would say that basically everyone I got on the phone with, and even some folks on social media, have mostly expressed caution and skepticism. The data in these new papers show some measurements of, what happens when you pass electricity through this new material that could be a superconductor. They've also looked at what happens to it when you put it into a magnetic field. These are sort of very standard tests for superconductivity. If you have a superconductor, you basically know what should happen when you pass electricity through it and when you put it in a magnetic field. And there's sort of very clear signatures that you would look for in the data if it was a superconductor. And folks that I spoke to told me that they didn't really see those signatures very clearly in the new data. So not everyone I spoke to dismissed the claim completely, but basically everyone told me that some of the data looked unusual and at best inconclusive, and some folks had more critical things to say too.
So I imagine the scientists who worked on the study had something to say about that. Did they talk to you?
Yeah, I spoke to one of the members of the research team, and he was quite confident in their discovery and assured me that the paper is in the process of peer review and will eventually be published in a journal, so go through sort of a more rigorous scientific evaluation. And he also said that he'd support anyone who wants to replicate the measurements. So him and his team will keep working on perfecting the material and getting more data. And they're very open to the idea of other folks trying to cook up the same thing and run their own tests. But I want to add that, like, even here, there's a little bit of trouble. Like, as we mentioned, there are two papers. They both report on the same material, but it sounds like there's a little bit of internal conflict within this research team, which is why two papers ended up being uploaded to the archive. So I think we'll need a little more time to figure out exactly what the official version is.
So you're not betting on having a superconductor at room temperature and pressure in your home anytime soon then?
Yeah, I mean, this is going to be a really boring take, not hot at all. But science is a team sport, and we need more people to get on board and do their part before we can actually say something about a revolution coming up in superconductivity.
Let's take a quick break to tell you about some other great New Scientist podcasts. This week, everyone's talking about Barbie and Oppenheimer. Unfortunately, we haven't got a science angle on the Barbie film, but Christy did get an interview with historian Kai Bird, who co-wrote a Pulitzer Prize-winning biography of the atom bomb scientist J. Robert Oppenheimer. It's a really fascinating insight into one of the most important scientists of all time, and whether or not you've seen the film, you should definitely listen to that interview, which you can find on your feed now.
Plus, we're continuing the fun of Dead Planet Society, a 10-episode exploration of how to break our solar system. The newest episode asks, could we ever drill a hole all the way through a planet?
Digging a hole through a planet is incredibly hard or near impossible. The main problem is temperature, because as soon as you start to go below the surface of a planet, there's going to be remnant heat from the formation of that planet. And so very quickly, you're going to rise to temperatures that are way above the melting temperature of metals.
Okay, so if we're using anything metal to drill this hole, it's going to become Gumby and then melt.
As usual, the answer relies on a lot of real science, but also incredibly imaginary situations. That's coming on Tuesday.
And you can still take advantage of a really great subscription deal for our magazine. 10 weeks of issues for £10 or $10. Get that by the 10th of September.
Find the details on our website, newscientist.com/podcasts.
We've been reporting on a lot of incredible weather records in the past few weeks, including the ongoing heat waves in the Northern Hemisphere, which have been driven by record high sea surface temperatures in the Atlantic. In South Florida, those highs have been reaching over 32 degrees Celsius or 90 Fahrenheit, and one sensor by the Everglades registered a temperature of 38 Celsius or 101 Fahrenheit, and if confirmed, that would be a new record for the hottest sea surface temperature we've ever seen. Christy, you've been looking into efforts to save one potential casualty of these bathtub hot waters, coral.
Yeah, it's been a truly all-hands-on-deck effort this week in the Florida Keys, which is this string of little islands at the very southern tip of Florida. Coral gets heat stressed at temperatures of about 85 Fahrenheit, which is about 29 Celsius. And since we can't really cool off the ocean, scientists from universities and nonprofits who are growing coral in these offshore nurseries are having to bring their corals to cooler waters on land. These nurseries, by the way, are the seeds of the entire effort to restore Florida's reef, which is the only one like it in the entire United States. It's been eroded by a lot of environmental stresses over the years and is already at only about 3% living coral at this point.
That's a shockingly low number. What are they trying to do to help?
Scientists at the marine laboratories and coral nurseries in that area have been essentially removing as much coral as they can from the water and transporting it to land-based facilities in the Keys and back on the mainland. I talked to Cynthia Lewis, who is director of the University of South Florida's Keys Marine Lab, and she described it as this almost military rescue operation.
Each organization has their own flotilla of boats and divers. So, you're talking about dozens, if not hundreds of divers up and down the reef that are working in their individual areas of expertise in their individual nurseries, and then coming together, transporting them in giant igloo coolers. I'll try to describe this, in giant igloo coolers, sloshing with corals and waters onto the boat, and then racing to the dock, and then transporting those coolers into pickup trucks and vans to get them here to the lab. Meanwhile, doing water changes, trying to keep that water, putting ice bottles in the water to try to cool that 90-degree temperature down slowly to something more stable. And then they have to acclimate them to get them down to the 85 degrees that we're holding them at before we actually put them into the table. So that process can take an hour to an hour and a half to slowly get those corals down to where it's not such a shock to their system.
At this facility, you can picture thousands of little coral fragments in dozens of big saltwater tanks, and they're making room for more by sending some to facilities further away in this specially fitted coral bus that's got all these special chillers and water pumps on board.
Sounds like quite an intricate process. We've heard so much about coral bleaching and dying over the years, but why exactly is hot water so bad for coral?
It starts with a little bit of Coral 101. So coral isn't actually one creature, it's two. Coral itself alone is very, very white, but it gets color from an algae that lives inside it, which also provides something like 90% of the food it needs. When the water gets too hot, the algae jumps ship and the coral starts to slowly starve. That's what bleaching is, and we're already seeing that in Florida from this heat stress, which can also make corals more susceptible to disease. And there's one in particular around Florida called stony coral tissue loss disease, which is a big problem already for them. The good news is that if the temperature stress doesn't last too long, the algae will come back, reestablish, and the coral won't actually die. So that's why bleached coral can still be safe, and often is, and we're hoping that we'll see this in Florida this year.
So we're in July now, so there could still be high temperatures for quite a while. And when exactly do we think that things might get better?
Unfortunately, it's a marathon, not a sprint. Lewis told me these water temperatures are the sort they usually don't see until August, and it might be September or later before things start to cool down significantly. So this is likely to be a weeks-long marathon to save as much as they can, which is unfortunately bad news for the coral on the reef itself that's not part of these nurseries, and it's also emotionally just really difficult for the researchers down there. Coral might not seem like the cutest of research subjects, but they do love this animal the way other scientists might, a bird or a mammal that they're studying.
Yeah, I mean, it sounds exhausting just to listen to. I can't imagine doing all of that work in the hot sun.
It is a slog, it sounds like, but Lewis does say that there's some good that could come. All the coral that they rescue that survives is going to go back into nurseries once the water cools down. And since one of the big efforts underway right now is to sequence genomes and breed corals that can survive at higher temperatures, she's hopeful that we might find more genetic resilience in the process of saving what we can this summer.
The corals of the future, and being able to save these corals, save as many of them as we can to be able to breed for stronger corals. First off, these corals that do survive maybe just a little bit more resilient to these impacts right now, the climate in the water that we're feeling. So maybe they've already been through those bottlenecks and they've survived to this point. So there's something about them that they have a little bit more strength, a little more resistance. And then if we can breed them, as many of the partners have been doing in these land-based nurseries, so we can breed these corals to perhaps some of their babies, will be even stronger. And I think that's really the future of this whole thing, that we may be looking at this horrible, tragic event, but on the other side of it, I think there is some hope. We're not giving up hope. That's the hopeful part. Nobody's giving up hope. Everybody's continuing to work to making this better so that the corals can perhaps survive the next round of this event a little bit better.
Freelance journalist Sophia Quaglia is here now. Welcome to the podcast, Sophia.
Hi there, thanks for having me.
Now, I hear you're about to completely change the meaning of Twinkle, Twinkle, Little Star.
Yeah, that's right. Take a listen to this.
What are we hearing?
Okay, so that is a sound representation of a star twinkling. That is getting slightly brighter and fainter. But instead of the apparent twinkle we see with our eyes when we look up, which is because of the way our atmosphere can make the light from the star kind of wobble on the way to us here on Earth, this is the star's actual innate twinkle. In the case of massive stars, it is the brightening and dimming of a star, and it happens because there are hot and cold gases inside of its core that basically wrestle each other, and they churn and they mix and they get pushed outwards in ocean-like waves. some gas waves make it all the way to the surface of the star, slightly tweaking its temperature, and as a result, its bright glimmer over the different periods of time.
I really like that. And I like this concept of innate twinkling. I like to think that maybe I also twinkle innately. This is incredible, though. It's got this kind of rhythmic hum to it, that sound we played. What's the story behind that noise? How was it made?
Evan Anders, a researcher at Northwestern University in Chicago, has basically found a way to model the movement of these gases inside the stars, which astronomers know has to be happening, but they hadn't really found a way to measure them precisely before. So this sound is basically a mathematical representation of those gas ripples making it from the core to the surface of a very massive star, 40 times the mass of the sun. He's also modeled the same thing for smaller massive stars. So here's a star that's actually only 15 times the mass of the sun.
Only.
That's super eerie. And here's an even smaller one that's only 3 times the mass of our sun.
That's amazing. You can really hear the difference in mass, and it gets higher pitched almost as it gets smaller.
Yeah, that's exactly it. And Anders said you can think of them literally as musical instruments.
A violin and a cello are both string instruments, but a violin is smaller and has higher pitched noises, and a cello is bigger and has like deeper noises, right? So just like that, the smaller stars, quote unquote smaller, they're still like much bigger than the sun, but the smaller stars in our study are more like the violin, where they have like some more high pitched noises going on, because they have basically like a smaller wave cavity, just like a violin has a smaller wave cavity. And our larger stars have a bigger wave cavity, just like a cello has a bigger wave cavity, so they have some deeper noises going on.
Of course, there are still so many other elements that might actually affect a star's innate twinkling. So scientists still need to factor in the effects of the magnetic fields inside the stars, the effects of star rotation, for example. But I think these findings can really be used to improve our understanding of how stars are built on the inside and how they spend their life and evolve.
So you said that astronomers haven't found a way to observe this directly yet. So how does this model work if we can't confirm that it's correct?
One of the big reasons we haven't been able to observe twinkling directly yet is instruments. We just don't have the right ones on Earth to look at stars for this data. Knowing the exact twinkling strength and interval is important because it tells experts what kind of telescope they need to actually find that twinkling. So if a star doesn't twinkle as much, they're going to need a bigger telescope to notice the twinkling. So Anders thinks that having this model will give astronomers a better picture of how to look at these stars to actually start seeing the twinkling. If you model it, they will come, basically. And Anders is really excited about being able to link his work in theory to the people out there who are observing the stars themselves.
I have been doing science for 10 years now. I've never really had many results before where I can go to a different community, like a community of observers, and say, I think you should see this. Can we test this? But this time we actually do have a way of saying, I think we should see this. Can you test this? Or if observers come to us with, hey, we have this weird observation. We think it's this. Is it that? We can also determine yes or no. Is it that thing? So that's the thing that's really exciting to me, is the ability to connect these two different groups of people.
Next up, a peculiar story from Jason Murugesu about the fact that we all seem to be very bad at estimating how much our hands weigh and why we might struggle to do this. Hey, Jason.
Hey, one question for you, Sam. How much do you think one of your hands weigh?
So, do you mean if I just hacked it off with a cleaver and put it on a scale? I can't say I've ever thought about it really. So my hands are on the small side, but I'd say it's about the same size as a thin sirloin steak. So I'm going to say about 200 grams or so, or maybe half a pound if you're using imperial units.
The average hand actually weighs around 400 grams. That's about a pound in America. Or for a more universal measure, how about a tin of chopped tomatoes? But yeah, Sam, you did what everyone in this study I reported on basically did. You underestimated the weight of your hand by about 50%. In other words, your hands are about twice as heavy as you think they are.
I clearly just don't know my own strength. But this study, they didn't just ask people to how much their hands weigh, right? So how did they figure it out? How did they get people to estimate it?
Researchers at Birkbeck University in London tested 20 adults who were each told to relax their left arm on this sort of pillar, kind of like an armrest. Initially, each person was told to let their hand hang freely, but then it was given support and a weight was attached to their wrist. None of the participants could see their hands or the weights because they were covered by a screen. The researchers asked each participant to judge whether their hand or the weight was heavier, and they did this repeatedly with different weights. Using all this information, the researchers were able to estimate with better accuracy how much the participants actually thought their hands weighed. Using this method, the team found that people underestimate their hand weight by 49.4% on average. Basically what you did, Sam.
I feel like I would have guessed about the same. I also have small hands, but I'm also over here now just wondering what all my other limbs weigh. This is this is just such a cool concept. So, why do the researchers suspect we are so bad at judging, I guess, our own bodies? You know, is it something to do with like our wrist muscles just being really strong or something?
They don't know, they're unsure. Our sense of how much our body parts weigh is super different to how we judge the weight of objects out in the world that we may pick up. We aren't basing our hand weight on any external sensory signal. This underestimation, they suspect, may make it easier for us to move freely in the world. Like, if we thought about the fact that we have 2 tins of tomatoes for hands, maybe we'd want to move them less.
I'm just going to go by Christie's soup hands now. That makes total sense. Did the researchers look at anything else related to this issue as well?
Yeah, they also looked at what effect fatigue has on our ability to estimate hand weight. They took another 20 people and repeated the same experiment, but this time they followed this up with a hand exercise that the participants had to do for about 10 minutes. Basically, they repeatedly squeezed one of those handheld dynamometer thingies that people use to improve grip strength. Pre-exercise, this group underestimated their hand weight by about 43.9%, but post-exercise, they only underestimated their hand weight by 28.8%. It means that feeling tired literally does make your body parts feel heavier.
That's it for this week. Thanks so much for listening.
As always, our show notes have links to all the fantastic new scientist reporting you heard about on the show today. You can subscribe to our show on whatever app you're listening on, and thanks so much for your support. Bye for now.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.